1,000 related citations on behalf of Dr. Kardi Teknomo. Such is the brief history of Dr. Kardi Teknomo that I got. Now is the time for us to listen carefully for his explanation in the form of a scientific presentation on the topic of ideal flow network for supervised learning. Dr. Kardi, the time is yours.
Okay, thank you. Okay. I will share my screen. Okay, so this is my invitation. So just close this. Okay, first I will demo first. Okay, so what we are going, before we make the presentation, let's demo first. So this is the website of IFN in Trevoledo. So you can check this. Anyway, this meeting is recorded, right? So you can check back again the address. Okay. So this is the demonstration of music generation based on ideal flow network. So can you hear this? Okay, that is a Mozart song, right? So, and when we use this Mozart song and then we put that into IFN, okay, so I will generate the music here. This is the original Mozart song. So I generate, this website will automatically learn, and then we can generate, okay, and then we can play back. Okay, so these are examples that we can generate music, okay, which is based on the original song with this Mozart. Right? You can hear that this is similar to Mozart song, right? So let's now go back here. I will have a sample music of Burung Kakak Tua, Indonesian music song. I think you are familiar with this. All right. Okay, I will stop this. Okay. Now using Burung Kakak Tua, so now you generate we let the IFN learn and then generate some music for you. Right. So we can generate other songs based on Burung Kakak Tua. So this is just to demonstrate, right? What happened is, when we include, okay, when we include certain song, for example, Mozart, right, then we train the IFN or the AI in this case, right, or the machine learning in this case, right, and then it will generate automatically with this similar to the original music. Okay. Now, if we train another music, for example, Burung Kakak Tua here, then it will automatically generate, okay, another kind of music which is similar to Burung Kakak Tua. Okay. So this is what AI is about. So instead of we do programming of this music, right? So we train the data into the AI system, then it can learn from this, and then it can do something about this, like generate something, like generating of music. So let me show you another demonstration here. So I have here the spider. Oh, wait. So let me share the screen again. Okay, not based on music, now based on spider. So this is the demo of IFN for machine learning. Can you see it? Right. So let's say you have a table. Okay. Say this is the usual table. So I will load this table. So this is the table of buying computer. So this is from textbook, right? So we want to know whether the people will buy computer or not. And these are the data, right? We have input data of age, income, okay, students, and credit rating. And then the category here is buying computer or not, yes or no. Okay, so this is the data. Let's train this. And we will get a visualization of IFN with this yes or no. That means yes mean buy computer, no mean no, don't buy computer. This kind of student. Okay, and now what happened is you see the precision here is 85%. Now we can predict using the new data. Okay, so for example, this is a new data set, and we can predict, and it will predict whether it is will buy computer or not, right? So this and each prediction will have certain confidence. Now using IFN, unlike the usual classifier, right? Using IFN, you can also generate. Okay, so for example, what kind of features that actually create? See, when I said okay, we set the generate for class yes, we can generate the data back using IFN. Okay, so let me demonstrate another example here is transportation mode. So this is the data. So whether the people will use bus, train, or car, right? And these are the data. So the gender is male or female. Car ownership, how many cars do you have? 0, 1, 2. Okay, what is the preference of travel costs, cheap, standard, or expensive, and the income level. Okay, so these are the data, and we train this. Okay, so then we get three type of IFN. Yeah? So this is the train, this is the IFN for bus, and this is the IFN for car, right? And the result of the training is actually how many percent? Oh, 100% precision. Right? Okay. And now using this, we can generate any data. Okay. So, and say this data, okay, gender is male, car ownership is 0, travel cost standard, income level medium, that kind of person will use train with probability of 52%. Now, we want to know what is the other way around. So the inverse function, meaning that we want to know what type of features that or what type of people that actually use car. Okay. Then you will see we can generate back the data, okay, using mostly female and car ownership probably 1 or 2. Okay. And travel cost is expensive usually. And look at this, the generated class of data is not actually inside the original table. Okay. So this is the capability of IFN to generalize the data, okay, based on the training result. Now, we can also do IFN for image processing. So I will close this. Okay, I will close this process. Come back again, image processing. Okay, so this is the binary image processing. So this is 1, right? And this is E, right? And what is this? This is A, right? F, and so on. So when we ask IFN to predict, of course, it's 12% predict F. So how about this? Is correct, but how about this one? Oh, it's wrong, right? So, but why it's wrong? Because we did not train yet. So let's train that. Okay, so this is the training quite fast, right? So accuracy 100%. So let's predict that. Oh, now become I. Okay. So again, this is E. Let's predict. Oh, that's correct. E. Oh, let's delete this. Okay. Let's check whether the prediction is correct. Oh, IFN predict wrongly. This is said is P. Actually, should be F, right? Okay. So there is possibility of error. So and then he said, okay, let's train that. This is not P, this is F. Okay, let's train that. Okay, train with new label F. Okay, now we predict. Previous data. Now we have this one. Oh, this predict E. Okay, this is empty. How about this one? Oh, it's predict correctly A, right? So how about this one? Oh, it's predict correctly P. Okay, so we can use IFN for predicting the image. Now we can demonstrate also that the IFN can also do text processing. Okay, and oops. Okay, let's say I have a Indonesian story here. Okay, this is from Asmaraman Kopingho. Probably some of you familiar. And based on the training that we have done this, the training is quite long. Okay, it can generate stories. Okay, IFN can generate different stories. So depending on how many sentences do you want, it can always generate. Say I have only one sentence, it will create stories. Okay? So I can also create, say, I create a poem here, right? And it can generate a poem. Okay, so these are the demonstration of IFN. Okay, so let's go to the actual course here. So just to give you some motivation. So this is today's talk. I'll discuss about IFN for supervised learning. Okay, so I have demonstrated this. So if you look at this demonstration a while ago, what are the things in common among those applications? Right? So the things in common are, they are actually all application of IFN classification. Right? So then in this lesson, we will discuss how we will utilize IFN for supervised learning, pattern recognition in data science. And of course, first we will discuss what is supervised learning, right? In this case, I will discuss regression, classification, and then I will discuss about IFN itself. And then how we will apply this IFN for classification. Okay? Okay, so these are actually many names of similar field. So when you hear the name nowadays, artificial intelligence, data science, business intelligence, multivariate analysis, computational intelligence, machine learning, statistical learning, data mining, pattern recognition, they are all actually very similar to each other. Okay, almost there is no difference. So when you talk about pattern recognition, you know they are actually talking about basically in the old days. Okay, when I started my master degree, or they call it multivariate statistics actually. Okay. Nowadays they rename it to different name, but they are actually the same thing. Okay, so let's call this data science. So there are several major tasks in data science. So one is supervised learning, the one that we will discuss today. The other one is unsupervised learning, semi-supervised, association, feature selection, and anomaly detection. So these are the books that you can read by yourself, okay, that actually discuss all of this in more detail, right? So what we discuss today is only supervised learning. Okay. So what is supervised learning? So now you have a pair, okay? Input and output. And then supervised learning is basically a function that maps the input to the output. Okay? You have data of input and output pair. You put that into the function, okay? Then it can produce some parameters. Based on that function and parameters, then you can either classify or do some kind of regression. So there are many methods in supervised learning, including decision trees, naive Bayes, right? SVM, artificial neural network, logistic regression, and so on and so forth. Okay, these are a few of them. Okay. In contrast, we also have what is called unsupervised learning. What is that? Now you have only the input without the output. Okay, and using unsupervised learning is a function that form cluster, a natural grouping. Okay. They call it unsupervised because it seems like it self-discovered the natural pattern in the data set, which basically based on distances. So example, hierarchical clustering, K-means clustering, PCA, and so on. Okay. Now, let's go now into supervised learning. Okay. What is supervised learning? Again, we have a pair of data, X and Y. X is the input, right? Y is the output. Yeah? The input is a matrix, the Y, the output is usually a vector. Okay? Now, when we say supervised learning, okay, is a model function f that can be calibrated to get the model parameter alpha so that the y equal to a function of x and the parameter alpha. Okay? So when we say calibrated or training, okay, that means you have the x and y and the function, you want to get the parameter alpha. Alpha is a vector. Okay. Next, when you said, I want to predict using supervised learning, what does it mean? It means, okay, using that function and that parameter that you already have, you have calibrated already, okay, then you have a new data, new input x here. You put it into the function, you get the prediction y. That's the meaning of prediction. Simple as that. Okay. So there are two possible learning models in supervised learning. One is called regression. The other one is called classification. What's the difference? The difference is actually only the data type. Okay. When your output, which is the y here, is real value, continuous value, okay, that is called regression. Okay. When your y or the output here is categorical, okay, discrete value, okay, then this is called classification or pattern recognition. Is it clear? Okay. So in both model above, okay, the x can be any type of pattern. It can be real, can be categorical. Okay, so you understand what is the meaning of supervised learning, right? So, hey, what is learning? Okay. So a system, we call this a system learn a pattern, okay, if that system actually encode that pattern into its structure. So the system structure changes as the system learn that information, that definition. Okay, so in statistical term, learning means calibration. That's it. Right? Okay, I will give you example in regression so that you can get familiarity. Okay. So say I have this data. This is the data used car, okay, second-hand car of the same type, say X by Z. Okay. So and we have data of age and kilometer, okay, and these are the price. Okay. So and we estimate using regression, multiple regression, linear regression model, price equal to A plus B times age plus C times kilometer. Okay. So the two influence factor with this age and kilometer to the price. Okay, this is the data. So, and we put this into matrix, right? So we have independent matrix and we have dependent matrix with the price. Okay, and then we compute using singular value decomposition, for example. Okay, so this is in Excel, and you get this value of parameters with this. Say 900 something minus 24 minus 20. Okay. So what is this? So now you want to check the error, so you can get the price, which is the output a while ago and you predict, right? And you minus between the price and the estimate of the price, you get the error, right? So if the age is 0, the kilometer is 0, that means the new car, right? Then the price is around 900,000. Okay. And this is in pesos. So now you can predict this. Okay, so if you have a used second-hand car, used car, okay, 21 month and has been driven for almost 15,000 kilometers, how much is the estimate price? So you can just compute that, plug into the numbers, and you can say, okay, that price, the price is 600,000, right? So now use this example of regression as machine learning. Okay, so the terminology only that is actually different. Okay, the data itself, we call this training samples, okay, or pattern, right? The output, which is the price, we call this teacher. Okay, the system, with this linear regression here, okay, the price equal A plus B plus multiplied A plus C times kilometer. That is the system. Okay, the learning algorithm here is, say, using SVD, right? And the parameters here, we call this structure. So only the terminology that make it different. Okay? Everything else is the same. So if you look at this, okay, training means learning, means calibration. The teacher means desired response. So the 3,800 here or 3,700 here is probably almost the same, right? So there is some kind of randomization here, but actually they are almost the same numbers. Okay? What happens if we divide these numbers of flow, okay, with the statistic of the flow? For example, the minimum or the average or the median, okay, or the total of the flow itself. Amazingly, okay, over time, okay, it will create a flow matrix with our integer. Okay, something like this, F in the bottom here. Okay, and not only they are integer or asymptotically integer, they also have a pattern that the sum of row will be exactly the same as the sum of column. You see here, you have 8, 3, 3, 16, 12, right? At the bottom also have 8, 3, 3, 16, 12. Asymptotically. Okay? This only happens when you run very long time. Okay? So this interesting phenomena, okay, regardless the number of agents or the simulation time, okay, N and T in here, when they are quite large to fill the network, okay, we have certain asymptotic values of the relative flow ratio. Okay? And this limit of the flow ratio, okay, this is what I call as ideal flow network. Clear, yeah? So these are the asymptotic value in the ideal form, which is the steady state, okay, in the limit, right? So now, what is IFN? Is the steady state relative flow distribution in a strongly connected network, okay, where the flow are conserved. So there are two main parts here. One is irreducible. What is the meaning? The network is strongly connected. Yeah? Second is premagic. What is the meaning? The flow are conserved. The sum of columns is exactly the same as the sum of row. Okay, so of course, because this is a network, you can either use a network digraph or you can use matrix. Okay, and to compute that without simulation, you can also use Markov chain. Yeah? So say I want to find the limit distribution pi, or given the stochastic matrix S. Okay, so you just transpose it and then minus with I is the identity matrix. Okay, we want to find the pi here. Okay, so the solution is actually using pseudo more Penrose inverse. Yeah? This, you form this matrix and then you can get that value. Okay, And well, wait a minute, you said, oh, I don't know how to compute this. It's fine, okay? You can just use the software, okay? There are some Python code available in GitHub. If you don't like using Python, you can also use Excel. So you just download this in the website, okay? And if you don't like to use Excel or Python, you can just use the JavaScript, okay? Which is also in Revolut website, okay? So yeah, it's also accessible in mobile. Okay, so don't worry about the formula. So these are the properties of IFN. Okay, so first is irreducible. That means the network must be strongly connected. Meaning from any node, you can go to any other node and go home to the original node. Okay, that's irreducible. Second is pre-magic. What does it mean? It means the sum of row must be the same as the sum of column in the matrix. Yeah. Optionally, as a modeling tool, you can connect this to the sync node. For example, what if my network is not strongly connected, but is weakly connected? Okay, there is a sync or a source node. Then you can add one single cloud node, just one single cloud node. Okay, from the sync node, you connect to the cloud node, come back to the source node. Then automatically it will become irreducible. And because ideal flow is a relative flow, right? Then you can actually scale up or down easily, okay, by any positive value, global scaling, to produce the equivalent of IFN. So these are the properties of IFN. Okay. Okay, let's make a game. Okay, I want you to do a simple practice here. Okay. First, you create any network, okay, but the network must be strongly connected. Okay. Each of you, can you make, say, 3, 4, 5 nodes? Okay. You create a strongly connected network. Okay. Remember, strongly connected network means you can start from any node to go to any other node and go back to your origin node. Okay, and then you create a random cycle. Okay, that means random path from the home node to any other node. Okay, and then find the path, go back to your home. Right, and then now you record the trajectory path in its link by tallying the count of the flow in its link. Can you do that? You do it several times until each link contains at least one trajectory. Now, show me, okay, now you put that flow into matrix and then show me what happened to the sum of row and the sum of column. Can you do that? You have paper and pen? You want to practice? Okay, let's do it in whiteboard. Can you see the whiteboard? Can I get your feedback? Okay, yes, so I have, okay, good. So I have A here, I have B here, I have C, I have D. How many nodes you want? 5? Okay, I have E. Okay, so I want to create a strongly connected network. So from A, I can go to B, from B, I can go to E, and then go to D, go to C, go back to A. So this is strongly connected already. But let's make it more complex, okay? So from here, I can go here, I can go there. Example, okay? Say, tell me, where is your home? See, in A, right? So let's say you want to go from A to B to E to D, C, and back to A, okay? So from A to B, you count 1, right? And then from B to E, you count 1, right? And then E to D, you count 1, D to C, you count 1, and then from C to A, you count 1. So that's one cycle, right? So let's go, let's make another cycle, okay? So So say I have another cycle from C to B, I count 1. And then B to D, I count 1. D to C, I count 1 again. Okay, let's make another cycle. Where do you want to start?
B to C to D.
Okay, let's go from D to C, and then from C to
D.
C to D cannot. You see, there is no arrow from C to
A to E.
to A. Okay, and then to B,
Yeah.
and then original
E.
to E, and then go back to D. Right, go home.
Yeah. Yes.
Okay. Okay, from here, let's say. Okay, let's make the matrix of this. Okay, so I have a matrix of A, B, C, D, E. Okay, and then here I have A, B, C, D, E. Okay, so tell me from A to B, how many?
2.
2. Okay, 2. From A cannot go anywhere else. So B to D.
B to
3.
D.
1.
1.
B to D is 1, right?
1. Yes.
Very good. And then B to E,
2.
2.
2.
And then from C to A is
C to
2.
2.
C to B.
1.
Okay, very good. And then from no more, right? And then D go to
C.
D. How many?
3.
3. Very good. Now E go to
D.
D. How many?
2.
2.
2. Okay, very good. Is there anything else? None, right? Okay, now you sum. Sum to the row, sum of row and sum of column. So you get 2, 3, 3, 2.
2.
And then sum at the bottom. 2,
3.
3, 3, 3, 2. See? Exactly the same, right?
Okay.
Ah. So you get IFN. This is the IFN, okay? And what is the pi? The pi is the sum of this. 2 plus 3 plus 3 plus 3 plus 2. How many? 9 plus 4 is 13, right?
13.
Yeah, so the pi is 13. Easy? Oh, you know what is IFN, right? Okay? Is it clear?
Clear, sir.
Yes.
It clears.
Okay, so you can create any random network, okay, and you will always get that kind of properties. Amazing. Okay, if you are not making a cycle but a random walk, so meaning the origin and the end is not the same node, it will not become pre-magic, right? But if you run it for a long time, it will become pre-magic. Okay, so
Pak Kardi, please give another example, maybe.
give another example. Okay, I can give you
Yes.
another example. Okay, so
Thank you.
here I give another example. Okay, so I have this network, very simple, A, B, C, D. Okay, I have these trajectories. If you look at this trajectory, what is this? This is all cycle, right? Can you see it? I have 6 trajectories here.
Yeah.
A, B, C, A, B, C, D, B. So the origin, oops. So if you look at this, the origin and the end is the same. That means a cycle, right? Always the same. That means cycle. Hey, there is B here and there is B here. That's fine. Okay, but the most important is the origin and the last one. Okay, so let's assign this. Okay, this is another example. Let's assign this. So I have the first trajectory, which is A, B, C, A. I put this A, B, C, A, right? This is A, B, C, A. So we go from A to B here, 1, right? And then B to C, 1, C to A, 1. So then I put this into the flow matrix. Okay, I can also divide the flow matrix, okay, with the sum of the on the right here. That will become the stochastic matrix. Okay, let's assign the second trajectory. What is the second trajectory? BCDB, right? So BCDB. So again, okay, B to C, one more, right? So 1 plus 1, so become 2, right? And then C to D. Okay, this one was 0, so add 1, so become 1. And then D to B. D to B was 0, now become 1. Right. So put this into the matrix, you get that flow matrix. You divide that flow matrix with the sum on the right side, you get the stochastic matrix. Clear? Right? You can continue this, right? The same thing, the third trajectory. Okay, you assign again, and then you put that into the flow matrix and the stochastic matrix, and so on. Okay, until the sixth one, right? The fifth one and the sixth one. Then you will see, if you compare, okay, look at the stochastic matrix here. In the beginning, you will see only 1, 1, 1. Okay, when you add more trajectories, now become 1 and 0.5, right? And then now become 1, 0.5 and 1, 0.25. In here, becoming more, once you put more trajectories on it, they are learning, okay? The probability changing become better. Actually, it's the 0.5 still 0.5, but 0.25 now becomes 0.17 here. Okay, 0.25 here becomes 0.33. Okay, when you add again, oh, it doesn't change, but the 0.5 now becomes 0.444, right? And then you add again, it becomes 0.45. So if I graph this all, you see they converge, right? The stochastic matrix will gradually towards some asymptotic value. That's how the IFN learning works. Is this clear or not? Okay, so basically this is mathematics, no? So you have the network, okay, and then you can assign flow into that network, okay. Eventually you get the probability here, right? Stochastic matrix in the probability, right? And automatically it will go to asymptotic value.
Kardi,
Yes, go.
sorry. Okay. Can we go to the previous
Sure.
example?
Yes, go.
Okay. If I exchange the node B and D,
If you change the node B
yeah,
and
D, do we have a result the same with the previous one?
no, it will not become the same.
Oh,
So
okay.
you need to first create the network first, right?
Yeah.
So and then you assign some cycle inside the network. So if you change D and B, for example, you do it this way, right? Instead of from D to B, now you go from B to D.
Yeah.
Of course, the trajectory does not apply, right? Because now you cannot go from D to B, so this one cannot be done.
If the link still the same?
Oh, if the link still the same, it's fine.
Okay.
Right?
I just exchange the B and D, but the link is still the same with the previous one?
Yeah, as long as the trajectory represent the actual network, that is fine.
Oh, okay.
Okay,
Okay,
so
thank you.
remember, you can create any network, random network. Okay, there are only one requirement which is strongly connected. What is the meaning of strongly connected? From A, you can go anywhere, but must be able to go home.
Okay.
Okay, from B, the same thing. Can go anywhere, must be able to go home to B. From C, you can go anywhere, can go back to C. That is important. Okay. then automatically it will become pre-magic when you assign cycle.
Thank you, Pak Kardi.
Yes. So I hope it's clear, right? The IFN is rather simple, right? So now, why we use IFN? Okay. Originally, I used this for traffic flow in the network. So you can check many publications of IFN. So using this, actually, we can solve traffic congestion in the world. Okay. So, but nowadays IFN is also used not just for traffic. Okay. So it's become one modeling metaphor, right? Or name convention, which is based on traffic, but now we can apply to many other fields as well. Okay, so some people in the Philippines, for example, use it for healthcare, so checking the virus, and in India they are using it for example, what is that? Industrial automation, and so on. So here I explain about how we use IFN for data science. Okay. 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 So the most important here is the meaning. Okay. As long as you have the problem that can be formulated as flow equilibrium in a strongly connected network graph, then you can start to consider, maybe I can use IFN for this. Okay. So what is the advantage of using IFN? You are guaranteed to get the steady state, right? And this is based on maximum entropy principle. So it's a well-known principle in physics, right? And the flow is always conserved. And the number of data is actually parsimonic, yeah? Minimum only. So you don't really need big data for this. Right. And what is the limitation? There are 4 assumptions of IFN. If one of them is not satisfied, then you cannot use IFN. So this is not panacea. Okay? So you cannot use IFN if the problem at hand is not system in equilibrium. If the problem at hand is not cannot be represented as flow. Okay? Or if the network is not connected. Okay? So it must be strongly connected, closed system. It must be about the balance of flow. Okay? And it must be about a stochastic local information, so it's Markov, and it must be a long-term equilibrium. So if any of this not satisfied, you cannot use IFN. But if all of this satisfied, yes, you can try to think, maybe I can use IFN. Okay? And how to apply IFN in your field? Okay? To apply IFN in your field, you need to define the meaning. Okay? Of the following terminology. What is the meaning of nodes or state in this case? What is the meaning of links or relationship between state in this case? What is the meaning of trajectory of the path? Okay, what is the meaning of flow or performance that you want to apply? So that depends on you. Okay, so you are the one who assign the meaning. So the IFN is just the mathematics that help you to compute. Okay. Now, let's now apply the concept of IFN for classification, right? For data science. Okay. How we will use that? Okay. So let's review again. The IFN is strongly connected network where the flow are preserved. Okay. It must be irreducible and pre-magic. You remember that? I keep repeating that. Now, when we practiced a while ago, we can form a network based on trajectory cycles, right? And it will always produce ideal flow network. Then we can use this property. Okay? We can use this property. How we will use this property? Then we can create from the data, you create a cycle. When you create a cycle, then you create an IFN. Then you can just use the maximum entropy, okay, to do this. So, how we will use IFN for classification, right? Well, IFN can be used for supervised learning, classification in this case, right? So, X represents, say, the matrix, the data table, yeah? And it must be discrete data type. Okay? Discrete means it can be numerical, categorical in nature, but it must be discrete, okay? Not real number. Second, the output must be, of course, it's because it's classification, so the output must be discrete as well. Right? Can be numerical, can be categorical, but must be discrete, yeah? Integer, not real number. Okay, so let's call this IFNC for short, right? So what is the characteristic? The characteristic of IFN depending on how you define the trajectory. Okay, so the technique is simple. You train per category, okay? And then the prediction is across category. So in that case, it's very nice because now if what happens if I have only one category, then you can also use for anomaly detection. Okay, so meaning that it is within the scope of network. Yes. And another nice thing about IFN is it's expandable. Okay, the network is expandable to the new category of the same input variables, right? And then per category label, you just use the entropy ratio. Okay, what is the advantage of using IFN for classification? This is called eager learning with parsimony data. So the number of data is very minimum. It's a glass box instead of black box, meaning, say, compared to neural network, okay, you don't understand really what is going on in deep learning, right? But in IFN, you can see visually what is inside the network. What is the decision that made by the IFN? So it's transparent, okay? And this is the nice thing. Using IFN, okay, you can also do approximate inverse function. That means you can generate the trajectory back. Okay. Another nice thing about IFN classification is now you can use higher Markov order, okay, to check the accuracy. Later I will discuss about this. Right? So next is you can abstract the network. And of course, you can also do feature selection similar to PCA using node analysis if you want. Okay, what is the disadvantage? Again, this is classification, okay, and only for discrete values. That means only categorical or numerical value or both, but discrete. Okay? So this is like decision tree. If your data is actually a real number, then you need to discretize first. Okay, and it's very sensitive to the way you read the trajectory. Say, if you want to read by column, for example, instead of by row, yeah, say you have the data table, so you read by column, you will get exactly the same as naive Bayes. Okay, but if you read by row, it's actually will get a better result. So I will show you here. Yeah, the general steps. Okay. Step by step. Number one, okay, you separate the data matrix into, you sort first, right? And then you put it into category. Okay, so one IFN is one category value. And then you read the stories, okay, by setting trajectories to train the IFN. So how do you read the stories? Read per row in the data table. After that, of course, you can get the stochastic matrix, okay. Once you train that finish, then you can do prediction, right? How do you do prediction? Again, you compute the trajectory probability from the path of the flow, okay? And then from the probability, you calculate the entropy, and then you get the maximum entropy. That's it. Okay, let's take example. Okay. So, a while ago I demoed this, so I will go more detail a little bit here. Huh? So I have a demonstration of table. Here is the transportation table. Okay, this is called mode choice. Okay, whether this person, so each row here represents one person, one respondent. Say you get from the questionnaire survey, right? So the gender is male, car ownership is 0, mean no car, right? Travel cost is cheap, that's the preference. Income level, actually the actual income, so you can categorize it into the discrete value become low, medium, or high. Okay, they use pass or train or car, right? So using IFN for classification means we read the trajectory data and then we store the information into the IFN. Okay, something like this. So because we have three classes here, bus, train, and car, then we will have three IFN. Okay, one for bus, one for train, and one for car. Okay, so how to do? Okay, again, yeah, one IFN for each class category. What is the node here? The node is the cell in the data table. That means variable and or value, right? The link. Well, we can imagine there is a connection between the cell in the data table. Okay, so, and then what is trajectory? One row of the data table or one column in the data table. If you are using text, so one word per node or one sentence per node. It's up to you to define the node, links, and trajectory. So say if you are using it for image processing, one cell represent, okay, one pixel represent one node, for example. Okay. And then we say, what is the flow? The flow, of course, the count of the trajectory. Okay. Optionally, if you want to make it irreducible, right? You want to make it strongly connected, then you can use a cloud node. Okay. Suppose your network is not strongly connected, then you can add a cloud node. Okay. So there are three things, right? Actually, in data science or in supervised learning is only two. Huh? One is training, the second one is predicting. But in IFN classification, we have three. Okay, one is training, second is predicting, the third one is generating. What is the meaning of training? You have the data space, which is the input and output. Okay, you train that, and then you get the parameter space. That means you get the parameter. Okay, what is the meaning of predicting? Predicting means, okay, you have the input, okay, and you have the model now, the parameter plus the parameter space. You want to get the output in the data space. Okay. Now generating means, again, you have the output, okay, and the parameter space. Then you want to predict the input. So this is an inverse function. Okay, so I put it into a simple function here. So say you have a model with this function of x is the input, okay, alpha is the parameter, y is the output, right? When you say training, what is the meaning? Okay, calibrating, right? So then you have the x and y, this is the input, this is the data, input and the output, x is input, y is the output, and then the function. In this case, the function is, of course, the IFN, okay? And then you want to get the alpha, okay? Alpha later is the parameter inside the IFN, okay? Second is predicting, okay? In predicting, you assume the model with this f and the parameter are invariant, meaning don't change. The IFN does not change, the one that you have trained a while ago does not change, right? Now you have a new data x, okay, small x here, and then you put that small x into the function using that calibrated parameter that you have. Now you want to predict the y. What is the label there? The y, you get the output. So the next one is generating, the control. Assuming, okay, that the inverse function of that function, the inverse function exists, okay, and they are invariant. Again, the calibrated parameter is already there from the training. Okay, now you have the output, the label, the class, the category that you want. You put it into the inverse function using that parameter alpha. Now you want to get back the output, the x. Okay, so these are the simple mathematics behind supervised learning. Okay, so then I can use that concept a while ago, so I can assign. In IFN, okay, to train, that means simply to assign, right? I have trajectory T, then I assign that trajectory into the IFN. Okay? To predict what I will do, I'll just do matching. Okay, I do matching of that trajectory, okay, among all these IFN, F1, F2 until F8. Then I get the maximum entropy by matching this. I get the category G. Okay. The third one is control, right? To generate, how to do that? Okay, I know the F, I know the IFN here, FK. Okay. Okay. From the FK, give me back the trajectory. This is just simple Monte Carlo simulation. Okay. So generation function is basically the inverse function. Okay. Now, we can generalize this model. Okay. So in practice, I will use what is called lookup value, okay, LUT, to identify the matrix so that easier to compute. And then from this LUT, we can also generalize into using certain parameter of, I call this parameter Markov order. Okay? The default is of course 1, right? Meaning 1 node per unit variable value in the class. Okay? We can set higher Markov order later. Later I will explain more detail. Okay, don't worry this. So let's do training. Okay, what is the meaning of training? You have a trajectory cycle. Okay, and then you assign that into the IFN. Okay. Predicting again. Okay, you have the trajectory and you already have many IFN matching only. Matching of based on the maximum entropy to get the class. Okay. Next one is to generate. Okay. Now from the IFN, you do Monte Carlo to get the trajectory. Okay. So how do you calculate the link probability? Easy. Yeah. The link probability is just the flow divided by the total flow. Okay. How do you calculate the entropy? Now you have the probability of the link, right? Along that path, you just multiply, right? Probability multiplied by the ln of probability, and then you sum all of that. You get the entropy. Simple, right? So, and of course you take minus so that the result is positive, right? So, and the network, I call this IFN is expandable network. So, when the number of nodes and links, okay, are not known, you can start with empty network. Okay, as you read the trajectory, the network is formed by a simple rule. Okay, what is the rule? If the link exists, add the link flow with 1. Otherwise, create that link with 1 flow. Okay, so using expandable network, you will create a true AI. Okay, because the AI does not know in the beginning. Okay, as you input new things inside the AI will create the network by itself. This is amazing. Okay, so but be careful, huh? This is based on graph theory. That means link cannot exist without node. Okay, so but node can survive alone. So you should know this is based on the graph theory. Creating a link also means to create a node. Yeah? So if you delete one node, then all the links associated with that will be deleted as well. Okay, so this concept of expandable network is very powerful because the network can grow, okay, based on reading the data. Okay? So We don't need to know the whole data set beforehand to create the brain of the AI itself. Okay? The network is represent the brain of the AI, right? So as the AI learn new things, okay, automatically the network is expanded based on what you put into this AI. It's a very powerful concept. Okay. So that means the AI can learn new things based on its experience without bound. Okay, without bound. That's important because that means they will become smarter and smarter. Okay, so how do you do IFNC? Okay? A strongly connected network formed based on the reading trajectories, either by column or by row. Okay, and then you assign that into the network. Okay, please recall that the random cycle in the random network a while ago that we played, okay, always form pre-magic matrix, even if you have only one cycle. Okay, and when the network is actually expandable, okay, then the flow matrix, which is based on the trajectory cycle, is always IFN, which is pre-magic and irreducible. Okay, so the flow matrix formed by this way is always ideal flow network. Okay, let's say a while ago we have this data set, okay, just 10 rows, okay, and the way we read the trajectory matters. You can read by column or read by row, okay, and because they are not cycle, right? So then we need to make a cycle. So how do you make a cycle? You add one cloud node. Okay, I will call the cloud node Z. Okay, so what to do? Or what is cloud node? Okay, cloud node is just a modeling way. Okay, so that you can have a cycle. Okay, remember, we need to create irreducible network, so that's why you need to form the cycle. Okay, why strongly connected? Okay, if you don't make it into strongly connected, you will not be able to create the trajectory cycle. Then you cannot get the inverse function. Okay, you can still predict, but you cannot generate. Okay. Now, and the prediction is actually inaccurate, not so strong. Okay, so that's why IFN is very important. Irreducible and pre-magic is important because of this characteristic. Yeah. Now, how do you test a network is actually irreducible or reducible? Okay, so if you use matrix, you have the I is identity matrix, A is in this case the adjacency matrix, and then N is the size of the matrix. You multiply. Okay, you form I plus A, and then you multiply many times until n minus 1. Okay, and then if the matrix is all positive, no, then it is irreducible. Okay, or strongly connected. If not, then it is reducible. So by definition, this is the reducible. B is reducible if there is 0 there. Okay, so let's make a textbook example. Transportation mode, mammal, by computer a while ago. So let's say I have this data. Okay, how do you define trajectory for classification? First thing first, you need to, this is the X, this is the Y, right? The X is the data, the attribute, the class, the output, okay, and the Y, okay? And then what you will do, you separate per class, okay? So you sort it by class, so you have bus, train, and car. Why? Because we will train one IFN per class category. Clear? Okay, this is the steps. Next, let's go to per class now. Okay, note in here is variable value. Okay, so I will put it into hash code. Okay, now per each row in the data table, you read from the cloud node to the first cell in the data table, second cell, and so on until the last cell of the attribute. of X, and then go back to the cloud node again so that you will create a cycle. As simple as that. Okay, and there's an advantage of this technique. Why? Because it's online learning, right? You will not waiting for all data to be collected. So you just get per row. Okay, and actually this will have better precision than if you read by column. If you read by column, meaning that you need to have all data to be collected first, right? So that you can read per column. Okay, so let's take example a while ago, this one, right? So you look at the first row here, male 0 chip low for the bus, right? So I'll put here, male 0 chip low for the bus. Okay, let's name it. Okay, the trajectory cycle that we will form is Z from the cloud node. Gender is male, so GM. And then what is this? Car ownership is 0, so C0. Travel cost is cheap, so T travel cost. C is cheap. And then income level I, low L. Okay, and then go back to Z. Okay, the mode, which is the class, is the IFN name. Clear? So remember, the trajectory will call each variable and value. Okay, so I just use the first character of each variable and the first character of the value here. Okay, so then you do this for all. Okay, then you assign. Okay, for all rows, because we have only 4 rows, so you put this, then you create this IFN for bus. Right? You see, right? So you can just put this a while ago, the same, yeah? You just assign one by one, and then you get the kappa here is the total flow. Okay, so because you know the total flow and you know the flow, you can calculate probability, right? Link probability is just the flow divided by the total flow. As simple as that, right? So again, you read for the car. Okay, only 3 rows. Okay, so gender, male and female, so GM and GF, right? From the cloud node, you go to GM and GF, and then go to the next. Car ownership is either 1 or 2, right? And then travel cost is expensive all, so it's only 1 node. And then income level is high and medium. So there are 2 to go to the high, only 1 to go to the medium. Yeah? So this is IFN for the car. Okay. And then this is IFN for the train. Okay. You see, you can do it by hand, you see. For the simple data table here, you can do it by hand. And then we test the data. Okay. So now I have a new X, which is not in the data. Say I have a female, no car, expensive travel cost, and medium income. Then I put back into the trajectory cycle, right? So that new data I put into trajectory cycle. So GF, C0, TE, and then IM. Yeah? So then of course the beginning and the end is Z. Then I see check bit using the train, using the car, and using the bus. Okay, so this is the link probability. Okay, and then we can calculate one by one. Yeah, for the bus, for the car, and for the train. Okay, we can check the probability. From the probability, we can calculate the entropy, and then you can see the percentage of the entropy. Right. So and you see the maximum entropy happen to car, right? 35.98%. So this subject, okay, this female, will use car. That's the prediction. You see, right? You can do by hand, yeah, in paper. So if you use computer, I will use a hash code. Yeah? So I will create what is called lookup table. So a while ago, the gender is male and female. So I will put gender female is A1, gender male is A2, right? Car ownership is 012, so I will put this B, yeah? B1, B2, B3. Travel cost, I will put C, So C1, C2, C3, and so on. So these are the hash code, these are the variables and the value. Clear, yeah? This is the lookup table. Okay. And now from the data set, original data set here, okay, and the lookup table, then we can create a transform, okay, data set into the lookup table, so that easier to check using computer. Yeah. So, and then the result of the training is in hash code. Okay, so something like this. Okay. So based on this training, then you can predict and to generate. So is it clear? You want to ask question up to here? The training, prediction, and generation.
Tadi,
Yes, go.
can we use IFN for a big data maybe?
Yeah, of course. There is no problem of the number of data. Yeah, you can,
If we have maybe so many dimension or attributes and put it to the matrix, I think it's
become very big.
very big. Yeah.
Become very big. So then you can set what is called lookup table.
Oh,
Right?
okay. So we use
Okay.
table.
So
Okay.
then become smaller. The
Yeah.
purpose of lookup table is actually to reduce the space, right?
Yeah.
So that becomes smaller. Because anyway, if they are the same thing, so you put it back into the hash code.
Okay. Thank you, Pak Kardi.
Right? Okay. Is there any other question? But the training, the predicting is clear, right? The generating is also clear. Okay. Very simple. Okay. In fact, you can also, based on this explanation, probably you can already do, oh, I can program this already, right? Okay. Okay, let's go to the next topic. Okay, Markov order. So now we want to generalize this AFN. Okay. What is the meaning of Markov order parameter? So look at this drawing below. Okay, there is a problem in IFN because sometimes you don't know what is the meaning of this. For example, the left drawing here, let me get the pen. Yeah, this left drawing here, I don't know, they are actually from ACCD or ACCE. I don't know whether that is actually from BCCD or BCCE, right? This is the example. So there is ambiguity after you train the IFN, okay? The original data, because you want to get the inverse function, right? So you don't know what is the original data after you train. There's an ambiguity. Okay, so if you want to train with improved precision, then you need to remove this ambiguity. Okay, then you said, okay, instead of one node, I can increase the node in the original node. So for example, instead of A, B, C, D, and E, now I can put one node is 2 letters. Now I put one node is AC, AD, BC, and CE. In this case, I remove this ambiguity. So in this case, I have second order, right? In one node, you have 2 letters. Okay. Of course, from 1 to 2 is easy. Then I can increase 3 letters, 4 letters, and so on, right? The letters represent variable value in the hash code a while ago, in the lookup table. Okay? So in this case, oh, I can increase the number of letters or the hash code. Okay? That is the Markov order parameter. Okay? What happened? If you put the highest order, it is the total dimension of the input data, then you will get rote memorization, right? Because basically you ask the IFN to memorize everything. Okay? Well, it will become overfit, right? Meaning the IFN is very smart for your data, but it cannot generalize. Okay, so let's give an example. Say I have a first order parameter with 5 nodes and 4 links, right? The arrow here represents the links, yeah, A, B, C, D, E. So I want to get the second order, what to do? Second order is just 2 letters, right? So 4 nodes and 3 links, okay? And third order means you have 3 super nodes and 2 links. Right? The fourth order means I have only 2 super nodes and 1 link. And the fifth order, which is the highest, everything is just 1 node, okay, no link. Okay. In this case, I have and memorize everything, right? So, say I have this data table here, okay? The age, income, students, credit rating, whether they will buy computer or no, okay? And then I will put this into the lookup table. So this is the lookup table, LUT, right? So you see here, the A represent age, B represent income, C represent student, D represent the credit rating, and E represent the buy computer or not, right? And Z is of course the cloud node, okay? And then now the original data table here, we put it into the transform table based on the lookup table. So it become shorter. So if you have big data, there is no problem because now the data is much smaller. Okay. Now what happened if I train this using IFN classification? Okay. If you use Markov order 1, the accuracy is only 85%. 85.7%. If you use Markov order 2, increase accuracy, of course, right? So you make the accuracy higher because the IFN can starting to, generalize and memorize at the same time. Okay. So you see here, this is second order because now you have 2 hash code, yeah, in 1 node. If you use Markov order 3, you see here we have 3 hash code in 1 node. Okay, is maximum. The accuracy is already optimum, which is 100%. Of course, because the data table consists of 4 nodes, you can increase, yeah, to Markov order 4. Okay. Again, the accuracy is of course 100%, but this is overfit. Okay. So let's take. Okay, until here, is there any question about Markov order? This is the next topic. Is it clear? Markov order mean. Now, if you use text, okay, now you have if you are familiar with NLP, yeah, natural language processing, there is what is bigram, trigrams, and so on, right? So this is exactly the Markov order. So meaning that now if you use IFN, you automatically can create bigram, diagram, whatever gram you want, n-gram. Okay, just changing the parameter only. Okay. Very easy. Okay. So let's go back to the slide. We'll go. So what happened? Now let's use this knowledge of Markov order, okay, to detect some inconsistency in the data. Okay. So there is a myth. I will start with the myth. Okay. In the myth of classification, say supervised learning. Oh, if I have any training data, if I put into the program, then you will say it always be able to classify 100%. No, this is a myth. Why? Because some data set is inconsistent, conflicting to each other. Then you cannot classify correctly. What does that mean of inconsistent or conflicting data? Say you have 2 rows, okay, in the data table having the same input, but they have different output category. So the input is the same, X, the output is not the same. They have 2 or 3, say, the bus, they are the same X, the same gender, the same income level and so on, but they use bus and boat, bus and train, for example. Bus and train and car, okay? So then, when you train using supervised learning, you cannot get 100%. Okay? If you get 100%, that's luck, based on luck only. Okay? Why? Because the data is inconsistent. Okay? What's the meaning of that? Let me explain in the simple mathematics. Okay? You remember function and relation. Remember, in function, you have one x can only have one y. Okay? In relation, okay, this is function, right? The pen. Okay, pen here. This is function. In one x, okay, you only have one y. Relation, in other one, one x you can have many multiple y. Okay, so the same thing. If you have one x and have multiple y, okay, your data is actually inconsistent. So you cannot have inverse function. So let's take example here. I have a data. This is from the textbook. Okay, this data set called mammal. Okay, so let's say mammal 2. That means only mammal and non-mammal. Okay, the data is whether this animal is give birth, lay egg, can fly, live in water, or have leg, yes or no. Okay, they are binary and 3 values. Okay, from there we can use the lookup table. So we have A represent give birth, B represent lay egg, C represent can fly, D represent live in water, and E have leg, and F is the class itself, yeah, mammal or non-mammal. Z represent the cloud node. So again, we transform the data into hash code. Okay, and then we apply this with Markov order 1. Okay, actually, yeah, the same data set actually appear in both categories, but at this point you don't know. You cannot see the inconsistency in the data if you use only Markov order 1. I increase it. Okay, in here you can start to see. Okay, there are actually the same data set that appear in both categories. This one, you see, A1, B1, C1. Yeah? The same node appear both in mammal and non-mammal. So you can start to see the inconsistency. Okay? But you need to trace it one by one. Okay? Oh, the same thing here, B1, C1, D1. You see, this is actually inconsistent data. Okay? The same row both appear in 2 categories. Again, this one, the 3, C1, D3, and E1. The same node appear in both categories. Now, if we use the highest Markov order, clearly we can see that this one appear in both categories, right? So A2, B1, C1, D3, and E1. So that one is appear in both categories. So in that case, you will see, these are the data set that I marked. They appear in both categories. There are so many data set that repeated in 2 categories. So in that case, the data is inconsistent, right? So IFN classification can be used to detect the possibilities of inconsistency in the data. How do you get that? Simple, okay? First, you set the parameter to the highest Markov order. How do you get the highest Markov order? The number of variables in your data set. Yeah? So, and then if you set that highest Markov order, what is the meaning? That IFN is already doing the rote memorization, right? Okay. In this case, the accuracy is not 100%. oh, look, using rote memorization, the accuracy must be 100% using your data, but it's not 100%. Then you it detect that, oh, that means your data is inconsistent. Okay? Of course, right? If you memorize everything, it must be 100%. If not, then something wrong with your data. So this is another example. If the mammal, okay, you can see this blue represent the data that is actually repeated. Mammal have repeated data with the bird, and fishes also have repeated data with the mammal. Okay, the red one is mammal repeated with the reptile, and so on. That blue is available, the same thing. Okay, so now if we set the IFN using the highest Markov order, it will help us to detect whether there is conflicting data. What is the meaning of conflicting data? That means there is a repeated input, but they appear in different categories. Yeah? Why it can detect? Because the highest Markov order means rote memorization. Okay? The IFN just memorize everything for you. Okay? Then the accuracy must be 100%, right? If not, then you know something is wrong with the data. Okay, so for the conclusion, right? So IFN classification parameter can be selected to trade off. Okay, you don't put IFN in the rote memorization, of course. Yeah? You need to trade off between generalization. Low order Markov will have generalization, but accuracy can be lower. Yeah? So higher Markov order produce greater accuracy, but you know, it's less general because of the memorization. So you need to trade off between the two. Okay, to achieve greater accuracy, then you need to clean some of the data probably. Okay, so for further research direction, so you are graduate research program, so you can apply IFN itself in various fields. Okay, so you can use for marketing, industrial automation, engineer, okay, and healthcare and games and so on. Okay, it's up to you to decide how to apply IFN. If you want to apply IFN for classification, there are still many possibilities. Okay, again, the possibilities are infinite. Okay, so you can apply to text, to color image, to poem, to stories, to anything. Yeah? In terms of the theory, so I think we can still have many rooms for developing IFN for unsupervised, semi-supervised association, reinforcement learning, and so on. Okay, so if you use IFN, so tell me your stories. Okay, so how do you use it, and so that I can also tell your story to others. Okay? So thank you very much. I hope to get to hear your question and a comment. Oh, I cannot hear you.
Thank you, Dr. Kardi.
Yes.
Very interesting presentation, and we got the new knowledge from this IFN. There may be some participant who want to ask a question. Welcome.
Yes.
You can talk directly. I want to ask Dr. Kardi, is it possible if we use IFN to predict congestion caused by the number of vehicles on the highway?
Yes, yes. In fact, the original IFN is used for that, and you can download IFN transport in GitHub. It's free. It include open source.
Yes.
You search in Google IFN transport. Okay? There's a software already to predict the traffic congestion for IFN.
IFN transport.
Yes, the name is IFN transport.
On GitHub, Dr. Kardi.
Yes, yes.
Okay.
Pak Kardi, one more question.
Oh, cool.
We use Markov order before we clean the data, or we have to clean the data first, then use Markov order?
No, you detect first, right? You detect using the highest Markov order, then you say, oh, there is a data that you need to be cleaned, right?
Oh,
So
okay.
the purpose of Markov order is to detect which data you need to clean, right?
Okay.
Okay.
So and IFN also, can we also use IFN for image maybe?
Yes, yes. I demonstrated earlier that we can use image processing for IFN, right? You want me to demonstrate again?
Yes, please.
Oh, okay. Okay, so let me share the screen.
That is very interesting, Dr. Erna.
Yes, yes. So let me share the screen. Where is it? Oh, what? Why am I still in here? Wait, wait.
We may need to transform the pixel maybe to number or whatever
Yeah.
before we
So I will just
classify the image.
in the image. In this case, it's very simple. It's just for demo. Can you see it? Where is the zoom? Yes, here. So I just use Python, very simple program. Yeah, I just demo it. Okay. So I have a demo of image processing. Okay, so this one. So in here I just can create. Yeah. So for example, I have I can create, what is this?
Cube.
One, for example, right?
Oh, okay.
Okay, I will create, this is E. Okay, so I will just
Yeah.
say it is E, right? So then I will ask IFN to create, oh, this is 8, this is it. So I ask the IFN to learn first, okay? So it is use Markov order 53. Yeah, it's very high.
53.
53 because how many is this one? 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 80 maximum. The highest Markov order is 80, but we use only 53. Yeah. So then we can predict. Oh, this is E. Right.
Oh, okay.
Let me just draw. So say I have I can draw any other things. So this is A, and let's predict. Oh, see, the estimated is A with 100%, right? So again, this is supposed to be F. Oh, F, right? So the IFN is, when they already learn, it can already predict correctly. Yeah. Okay. So of course, in here I can draw whatever I want, and I can
Yeah,
save
okay.
it. Okay. And aside from image on table, I can also do the image text processing. So this is like the I can use to create anything else. Nah? So say I have English greetings. That's what the parameter I can generate. Nah?
Oh,
I can generate based on that. I can also create the. I already create the poem. Okay, so I load and then it can create the poem. Nah? So I can say I have 5. So okay, yeah. Okay, so you can just create. And a while ago, I also do the, what is that? The music. The music is not in here. It's already in the website. Can you see it? So, okay, I will go to this one. Okay, in tutorial, I will put IFN, IFN there. I have the IFN tutorial. You can see the music. Yeah. This is IFN transport is there, and the music is there. Okay, and this is the music that we can generate. So I have say Mary and Little Lamb. Okay, right. Okay, I will stop it. So now this is the original music of Mary the Little Lamb, right? Now I can generate, this is the actual music. So I generate based on IFN, that means of training, and then generate on itself. So I can generate any music based on that Mary of the Little Lamb. So it's not the same as Mary of the Little Lamb, right? But it sounds like.
Yeah.
Okay, so using IFN, you can generate text, generate music. Okay, so I hope, I don't know what other things that you want to generate.
Pak Kardi, what the input you give for the music?
Yeah, this is the input. This is exactly the input.
This is the
Yeah, this is the note,
oh,
right?
okay.
So say, for example, I want to
Oh,
run
okay.
the bar. See, this is the note.
Yeah.
I can increase the octave.
Yeah.
So this is the note. C mean do, right? D mean
Yeah.
re. Huh? 5 is the octave. Okay, so you can type in here the input if you want, okay, and then it will sing for you. Okay, so say I have a burung kakak tua here. This is the input, right? So this is the input of burung kakak tua. Okay, and of course you can type any song that you want here, right?
Yeah, okay.
And then after that you can ask IFN to generate music for you. Okay, so this is based on burung kakak tua. Welcome. Right. So these are the examples of a few example demonstration that we can use IFN classification for many other things. Again, this is still in early state of research, so I hope you can also. The module is already inside my website, so you can just check there. Okay.
Thank
And
you.
also in
Pak Kardi.
GitHub, you can just search in Google. And in YouTube, there are many video about IFN, so you can also check.
Thank you, Pak Kardi.
Yes. Is there any other comment or maybe question? So I welcome.
Dr. Kardi, I've seen the web Revol Edu last night,
Okay.
and this website very interesting content.
Yeah. Thank
What
you.
is also interesting is that Dr. Kardi is a graduate of civil engineering.
Yeah, I used to be the graduate. I graduated from civil engineering for undergrad. Okay. After that, I continue transportation field, so transportation engineering. So that's why I created IFN based on transportation. Okay, so my research still in transportation basically, but I combine it with artificial intelligence. Okay. But along the way, I don't know God's will, so I move around the world, okay, in many countries. So I teach in Japan, for example, urban plannings, and then I moved to Europe for pedestrian simulation. I moved to US in Wisconsin to stock tradings, and then go back to the Philippines, and then in China, and so on. So different experience shaped me, and then I can see that, oh, this is interesting, and all things is come back to the basic science, yeah. So just mathematics, statistics, physics, biology, and so on. Okay. So
And Dr. Kardi was a director of SCM ICPC. That was
that's many years ago.
science.
Yes, many years ago. We joined the Olympiad of the programming, yeah, in Thailand at the time.
Thank you, Dr. Kardi. I think actually there are still many things that we want to explore related to IFN, but the event is nearing its end.
Okay. Yeah.
Thank you very much, Dr. Kardi, for the explanation and insight have been conveyed today. We hope this is not only the end of the meeting, but the first step of the cooperation that we can build together.
Yes.
Once again, a huge thank for you from all of us. Good afternoon, Mr.
Good afternoon, and thank you very much for your attention.
Kardi.
Thank you very much, Pak Kardi.
Bye. I will leave. Okay?
Yeah.
Thank you.